Hello, welcome to Mickey Techie. Learn as engineer, teach as champion. First of all, I would like to thank my family for their continuous support and encouragement of creating these kinds of technical videos in public domain. And I would like to thank my mentor, Professor R. Surendran from Government College of Technology, Coimbatore, for igniting me a spark of creating these kinds of technical videos in public domain. And I would like to thank Almighty my God for my good health and broad mind, and my friends, followers, and my dear students and subscribers for their continuous support and encouragement. Today's topic of interest is applications of Bernoulli's equation. We know that the Bernoulli equation states that total head at section 1 is equal to total head at section 2. That is, the total head which is equal to pressure head plus velocity head plus datum head so the combined these three forms is called total head. In equation we can do p by rho g plus v square by 2g plus z is equal to total head. So this total head at section 1 which is equal to total head at section 2. So this is the interest about the Bernoulli's equation. So today we are going to discuss about the applications of Bernoulli's equation. So the Bernoulli's equation, in case the applications of Bernoulli's equation is applicable in all case of incompressible fluid flow where the energy consideration is involved. With this content, the applications like Venturimeter, Orificemeter, and Pitot tube were the major applications of applying this Bernoulli's equation. So here we're going to discuss one by one how the Venturimeter look likes, how the Orificemeter look likes, how the Pitot tube look likes, and the difference between the Orifice and Venturi. All those things we are going to discuss. Here, one thing I want to discuss: this Venturimeter and Orificemeter is used to measure the discharge of flow. The Pitot tube is used to measure velocity of the flow. We know that relationship between q and the velocity. So discharge is equal to area into velocity. So with this equation we can find the discharge of the Pitot tube. And here one more thing: in Orifice and Venturimeter we normally use liquids, whereas the Pitot tube we normally uses gases. This is the one important thing we have to know. In Pitot tube it cannot measure the velocity of a liquid. So you have to notice this thing: the gas velocity can be easily measured by means of a Pitot tube. Okay, I hope you have cleared about the applications of the Bernoulli's equation. And here, this is the Venturimeter. In Venturimeter, it consists of three portions. One is convergent, throat, and divergent. Convergent, throat, and divergent. So this is convergent, and next is a throat, and next one is a divergent. If you see the length of the convergent, is always smaller than the length of the divergent. The length of the divergent or angle of the divergent is not more than 8 degrees, because if it exceeds 8 degrees the pressure separation is happens. We know that the pressure separation or the pressure gradient separation will cause a series of losses in the flow. Therefore the divergent length is more since the angle is less. So this is the interest about the Venturimeter. And in the Venturimeter, the pressure difference is found at the pipe or entry of the convergent on the throat. It is the difference between the entry of pipe and the throat. So these areas, say this is section 1 and this is section 2, between the section 1 and 2, using the pressure difference or YouTube manometers or a pressure gauges, the difference of pressure is being found out. After that, the using a formula and the area of the pipe and throat, we can easily found what is the discharge in the venturimeter. So in order to found the discharge, the actual discharge formula is Q actual is equal to CD into square root of 2GH into A1 A2 divided by square root of A1 square minus A2 square. So A1 square minus A2 square. This is the formula. We know that the theoretical discharge is equal to A1 A2 root of 2GH divided by A1 square root of A1 square minus A2 square. So this is the formula. The actual discharge equal to CD coefficient of discharge into Q theoretical. Therefore this formula come into picture. So as I said earlier, the area A1 and A2 are found by means of the diameters and H is the pressure difference. So from the equation, the total head equation, we are deriving these thing. Okay, so this is about the venturimeter. And next is an orifice meter. An orifice meter is a very simple in construction when compared to the venturimeter, since a single orifice plate is fitted in the flow stream, then the area is being deflected and the pressure difference before entering the orifice and just after entering the orifice is being measured, and as the same formula about for the venturimeter we used to measure and found what is the actual discharge. Here one thing you have to notice that here more amount of losses are being taken care, losses are being placed because of the sudden contraction of area and sudden expansion of the flow jet. These areas will get a vacuum or a dumble is there. Because of these negative pressures, the actual jet is being contracted again. If you see here, this is the orifice diameter, but the original jet diameter is this. So this contraction is called as vena contracta, the further contraction by means of a pressure difference. So that is called vena contracta. So this is the major issue about the orifice meter. That is why the coefficient of discharge of a venturimeter is always greater than coefficient of discharge of orifice meter. So this you have to know. Because of so many losses, it cannot get the maximum amount of the discharge, coefficient of discharge. We know that coefficient of discharge is equal to actual discharge divided by theoretical discharge. So here the theoretical discharge is more in the orifice meter, but in the actual case it is less. That is why the CD value is very low as compared to venturimeter. So the same formula as I said. So actual theoretical discharge is A1 A2 root of 2GH divided by A1 square minus A2 square the whole root. So the actual discharge is equal to CD of theoretical discharge. Therefore the formula is here. So here in the Venturimeter, the losses are very minimum, whereas in the Orificemeter the losses are maximum. That is called vena contracta is more. So, uh, so it cannot produce that much of coefficient of discharge, even though it is simple in construction. It is not advisable for measuring the discharge at anywhere. So when Orifice meter is more on theoretical one. So here is the difference between the Venturimeter and Orifice meter. Here the loss are very less, hence the value of CD is very high in Venturimeter, where in the Orifice meter the losses are more. Therefore the CD value, coefficient of discharge, is low. As I say low, it is about 0.6 to 0.7. Here I am saying 0.9 to 0.98, like that. Okay. And Venturimeter, it cannot be installed where the space is limited. In the Orifice meter, it requires very less space. And Venturimeter, it is costly for installation and replacement, whereas in the Orifice meter, its replacement and replacement is easier and cost is cheaper one. And Venturimeter, it is used for measuring the high rate of flows, where in the Orifice meter you are used to measure a moderate or low rate of flows. So this is the difference between the Venturimeter and Orifice meter. I want you to know. Next is a Pitot tube. A Pitot tube is used to measure a velocity of the jet or velocity at a point. Here, the the placement of the Pitot tube, that point is called as a stagnation point. The stagnation point. So this is the stagnation point where the flowing air is accumulated here. So that is why it is called as a stagnation point. In stagnation point at which the impact of pressure is to be there, where the velocity is zero. At the stagnation point, if you have to notice this, the velocity is zero, therefore the pressure is been maximum. So Pitot tube is used to measure the local velocity of flow stream. It is not the average velocity of the pipe or conduit. It cannot measure the average velocity. It can measure only the local velocity. So for finding the velocities, theoretical velocity is equal to root of 2gh, whereas actual velocity V actual is equal to CV into root of 2gh. So CV is the coefficient of velocity. So with this, I'm going to stop today's lecture. If you have any doubts, please let me know in the comment section, and I will put another video for clarifying your doubts. If you like the video, please like, share and subscribe my channel Meki Techie for the continuous updates about the mechanical basics. I hope you have enjoyed the video, and I would like to once again thank you all for the patient listening. Thank you.